You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Natural language processing, often shortened to NLP, is the branch of artificial intelligence that focuses on teaching machines to understand and work with human language. Unlike numbers in a spreadsheet or sensor readings, language is messy. It is full of ambiguity, tone, and context. NLP provides the techniques that allow computers to read, interpret, and even generate text and speech. It is the field behind translation tools, chatbots, voice assistants, and document summarizers. For a learner, it helps to think of NLP as the bridge between human communication and machine logic. It is the way computers can move beyond rigid commands into interaction that feels more natural. This makes it one of the most challenging areas in AI, but also one of the most transformative, since language is at the center of how humans share knowledge and express ideas. The history of NLP goes back many decades. Early systems were built using carefully written rules. Researchers tried to capture grammar and vocabulary in logical statements, and then used those to translate or analyze text. These rule-based systems were often brittle. They could handle simple sentences but quickly broke down when faced with the variety and nuance of real language. A classic example is literal translation, where phrases like, "the spirit is willing but the flesh is weak," would come out garbled when shifted between languages. The lesson from these early efforts was clear. Language is too rich and flexible to be captured entirely by handcrafted rules. While those systems were limited, they laid the foundation for later approaches that would combine linguistics with probability and learning. One of the first practical steps in processing text is tokenization. This is the act of breaking down language into smaller units that a computer can handle. Tokens might be words, subwords, or even characters. For example, the phrase AI transforms language could be split into 3 tokens: AI, transforms, and language. Tokenization matters because algorithms cannot easily work with raw text as humans do. By slicing language into pieces, systems gain manageable inputs that can be counted, analyzed, and transformed. In modern systems, tokenization often goes even deeper. A complex word like unhappiness might be split into un, happy, and ness. This lets machines generalize, even when they encounter unfamiliar terms. Morphological analysis goes one step deeper by examining the structure within words. Human languages build meaning not only through whole words but also through prefixes, suffixes, and roots. Take the word rebuilding. The root build shows the main concept. The prefix re signals repetition. The suffix ing marks the continuous form. Together, they express an action happening again. Many languages use such building blocks in complex ways. In highly inflected languages like Turkish or Finnish, a single word can contain what would be an entire phrase in English. Morphological analysis allows computers to break down these layers and understand how words are formed. By analyzing structure, machines can better handle the variety of forms that words take in real communication. Part of speech tagging is another foundational step in understanding language. It assigns grammatical categories to each word in a sentence. Consider the phrase, "the cat sleeps peacefully." The system identifies cat as a noun, sleeps as a verb, and peacefully as an adverb. This categorization helps a machine recognize the roles words play. It matters because many words can serve different purposes. The word book, for example, can be a noun in a book on the shelf or a verb in book a ticket. Part of speech tagging gives context, so the system can interpret meaning more accurately. It is like giving a machine a lens for seeing not just words but their grammatical function within a larger whole. Syntax parsing extends this process by analyzing sentence structure. Humans intuitively understand how words group together into phrases and how those phrases relate to one another. A parser makes this structure explicit. In the sentence, The boy kicked the ball. Parsing shows the boy as the subject, kicked as the verb, and the ball as the object. These relationships are critical for meaning. Without them, words are just a sequence. Parsing allows a computer to see the skeleton of a sentence, making it possible to understand who is doing what to whom. This is especially useful in translation, question answering, or any application where meaning depends on sentence-level comprehension. Semantic analysis focuses on extracting meaning from words and phrases in their context. Words often have multiple meanings, and understanding them requires more than grammar. Take the sentence, "The bank is by the river." Here, bank could refer to a financial institution or to the edge of the river. Humans use context to resolve this automatically, but machines must be taught to do the same. Semantic analysis connects words to concepts and interprets them relative to the situation. This is where language processing moves from structure into understanding. It is also one of the hardest challenges, since meaning often depends on subtle cues and shared knowledge that are difficult to encode. Pragmatics goes even further, focusing on implied meaning and intent. In conversation, we often say things indirectly. When someone asks, "Can you open the window?" they are usually making a polite request, not asking about ability. Pragmatic analysis helps machines interpret such subtleties. It also considers factors like tone, politeness, and cultural norms. For example, in customer service chatbots, pragmatic understanding is necessary to recognize frustration or urgency in a message. Without it, machines risk responding in ways that seem tone-deaf or inappropriate. Pragmatics shows that language is more than words and rules. It is also about social interaction, shared assumptions, and unspoken context. Early attempts at statistical language modeling often used a bag-of-words approach. In this model, a sentence or document is represented simply as a collection of words without regard to order or grammar. For example, the sentence, "Cats chase mice," would be represented the same as "mice chase cats." While crude, this method allowed algorithms to count word frequencies and make simple comparisons between documents. Bag-of-words models powered early applications like spam detection, where the presence of certain keywords was highly predictive. However, ignoring word order meant that these models missed important nuances of meaning. They were a step forward from rules, but still far from true understanding. Word embeddings represented a major leap in NLP. Unlike bag-of-words, embeddings capture relationships between words in a continuous vector space. Words are mapped to points in that space, such that similar meanings are located close together. For instance, king and queen would appear near one another, while dog and cat would form another cluster. Models like Word2Vec and Glove learned these relationships by analyzing large corpora of text. The result was a way for machines to measure semantic similarity mathematically. Embeddings allowed NLP systems to recognize that doctor and physician are related, even if they look different on the surface. This made applications like translation and search far more powerful. Contextual embeddings took the idea further by adjusting word meaning based on surrounding context. Earlier embeddings treated each word as having one fixed position in space, but in reality, meaning shifts. The word bank in riverbank is not the same as bank loan. Transformer-based models like BERT introduced contextual embeddings, where each word's representation changes depending on its neighbors. This made NLP systems dramatically more accurate in handling ambiguity, idioms, and subtle expressions. For learners, contextual embeddings are worth appreciating because they move machines closer to the flexibility of human understanding, where meaning is fluid and highly dependent on context. Named entity recognition is a task where machines identify specific items in text, such as people, places, or organizations. For example, in the sentence Barack Obama was born in Hawaii, the system marks Barack Obama as a person and Hawaii as a location. This ability is crucial in applications like search engines, digital assistants, and information extraction. It allows machines to connect unstructured text to structured knowledge bases, supporting queries like, "Who was born in Hawaii?" Named entity recognition demonstrates how NLP transforms raw text into actionable information, moving from generic words toward specific, real-world references. Sentiment analysis focuses on detecting emotional tone in language. A system might classify a movie review as positive, negative, or neutral. For example, "This film was amazing" would be tagged as positive, while "the plot was boring" would be negative. Sentiment analysis is widely used in business to monitor customer feedback, in politics to gauge public opinion, and in social media to track trends. It shows how NLP can move beyond surface meaning into the realm of attitude and emotion. For learners, it illustrates that understanding language is not just about literal content, but also about the feelings and perspectives it conveys. Machine translation is one of the most visible applications of NLP. Early systems struggled with grammar and idioms, often producing awkward or incorrect results. Today, deep learning-based models achieve much higher quality, translating between dozens of languages in real time. Services like Google Translate rely on transformer models that capture not only word meanings, but also sentence structure and cultural context. Machine translation highlights both the promise and challenge of NLP. It makes global communication easier, but it also shows how difficult it is to capture the richness of human expression across languages. The progress here reflects the broader evolution of NLP, moving from rigid rules to flexible, learning-based systems. Text summarization provides another practical example. It aims to condense long documents into shorter versions that preserve the essential meaning. There are two main approaches: extractive summarization, which selects key sentences, and abstractive summarization, which generates new sentences that capture the gist. Abstractive methods, powered by deep learning, are closer to how humans summarize, rephrasing content in more natural ways. Summarization is used in news aggregation, legal research, and any context where large amounts of text must be distilled quickly. It illustrates how NLP systems can not only analyze language, but also generate it in forms useful to human readers. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. The story of natural language processing can be traced through its evolution, from rule-based systems to statistical methods. Early researchers tried to capture every nuance of language in grammars and dictionaries, but these systems were too rigid to handle the messiness of real communication. The shift to statistical approaches in the late 20th century marked a turning point. Instead of relying solely on rules, algorithms began to use probabilities derived from large collections of text. For example, if the phrase New York appeared frequently, a system could learn that York often followed new. This allowed computers to make informed guesses about language patterns rather than depending on brittle instructions. The statistical era of NLP provided flexibility and scalability, proving that language could be modeled by analyzing data directly. It was not perfect, but it represented a crucial bridge toward the more powerful machine learning approaches that dominate today. From statistics, the field moved into the era of deep learning. Neural networks introduced a way to represent language in more nuanced forms, capturing patterns that statistical methods missed. Instead of simply counting word pairs or relying on probabilities of sequences, neural models learned to embed words and sentences in high-dimensional spaces that reflected meaning. This transformation enabled breakthroughs in tasks like machine translation and sentiment analysis. For example, instead of memorizing that dog often appears near bark, deep models learned a representation that linked dog with other animals and behaviors. The shift to deep learning brought dramatic improvements in accuracy and fluency, laying the groundwork for today's transformer-based systems. It also signaled a change in mindset. Rather than programming language knowledge by hand, researchers let machines discover structure directly from massive datasets. Recurrent neural networks became an early workhorse of deep learning in NLP. Their design incorporated loops that allowed information to persist across sequences, making them well-suited for tasks like speech recognition and text generation. For example, when predicting the next word in a sentence, an RNN could carry forward knowledge of previous words to inform its decision. However, traditional RNNs struggled with long-term dependencies. A word at the beginning of a paragraph could influence meaning much later, yet gradients often vanished during training, causing the model to forget. Despite these limitations, RNNs were an important advance. They proved that sequential context could be modeled effectively, and they laid the foundation for later improvements such as long short-term memory networks and attention-based methods. Attention mechanisms addressed many of the shortcomings of earlier models by allowing systems to focus on the most relevant parts of input sequences. Instead of treating every word equally, attention scores weighted some words more heavily than others depending on context. For example, in the sentence, "The cat sat on the mat because it was tired," attention helps the model recognize that "it" refers to cat rather than mat. This capacity to capture long-range dependencies improved accuracy in translation, summarization, and question answering. Attention also provided a measure of interpretability, since the attention weights could reveal which words influenced the model's decisions. This innovation paved the way for transformer architectures, which rely entirely on self-attention and have since become the standard in NLP. Transformer models represented a dramatic leap forward in natural language processing. Unlike recurrent networks, transformers process all words in a sequence simultaneously, using self-attention to capture relationships between them. This parallelism makes transformers highly efficient, while their attention mechanisms allow them to model long-term dependencies with ease. Models like BERT focus on understanding language by predicting missing words in context, while models like GPT specialize in generating coherent text. These architectures underpin nearly every state-of-the-art NLP system today, from conversational agents to document summarizers. The transformer revolution shows how rethinking architecture can unlock entirely new capabilities. For learners, transformers are important to grasp not only because of their dominance, but also because they illustrate how a single innovation, self-attention, reshaped the trajectory of an entire field. Pre-trained language models extend the transformer idea by training on vast amounts of text before being fine-tuned for specific tasks. Instead of building a model from scratch, researchers train a massive system on general text, capturing patterns of grammar, meaning, and world knowledge. The model can then be adapted to tasks like medical question answering or legal document analysis with relatively little additional data. This approach mirrors human learning, where general education provides a foundation that can be specialized later. Pre-trained models save time and resources while also delivering impressive accuracy. They represent the modern standard in NLP, powering many applications you encounter daily, often without realizing it, from autocomplete in your phone to translation services online. Question answering systems are one of the most visible outcomes of advances in NLP. These systems can take a query expressed in natural language and respond with relevant, context-aware answers. For example, a virtual assistant might answer, "Who is the President of France?" with the correct name, pulling from structured knowledge bases or text corpora. More advanced systems can handle complex queries, such as, "Who was the President of France when the Eiffel Tower was built?" which require reasoning across multiple facts. Question answering highlights how far NLP has come, moving from keyword searches that matched strings to intelligent systems that can parse meaning, connect concepts, and respond in ways that feel conversational. Dialogue systems represent another branch of NLP where machines engage in interactive communication. Unlike simple question answering, dialogue involves context, memory, and intent across multiple turns. Customer service chatbots, for instance, must remember what the user said earlier in the conversation and adjust responses accordingly. Virtual assistants like Alexa or Siri use dialogue systems to handle tasks ranging from setting alarms to providing weather updates. The challenge in dialogue is capturing the flow of conversation, including implied meaning, politeness, and interruptions. Recent deep learning models have made dialogue more natural, But perfecting this interaction remains one of the hardest challenges in NLP. For learners, dialogue systems underscore the complexity of human communication and the difficulty of replicating it computationally. Speech-to-text systems extend NLP into the spoken domain, converting audio signals into written language. These systems analyze sound waves, detect phonemes, and map them into words and sentences. They are used in transcription services, accessibility tools, and voice-activated assistants. Deep learning dramatically improved their performance, making it possible to achieve near-human accuracy in favorable conditions. However, challenges remain in handling accents, background noise, and rapid speech. Speech-to-text illustrates how language is multimodal, existing not only as text but also as sound, and how NLP integrates with signal processing to bridge this gap. This technology has far-reaching implications, from improving accessibility for people with hearing impairments to enabling hands-free computing. Text-to-speech systems flip the process, generating natural-sounding speech from written text. Early systems produced robotic voices that sounded artificial and difficult to understand. Modern neural models, however, generate fluid, expressive speech that closely mimics human tone and rhythm. These systems power applications such as audiobooks, navigation tools, and voice interfaces. By making written content audible, text-to-speech broadens accessibility and enhances user experience. It also demonstrates how NLP moves beyond analysis into generation, creating outputs that engage directly with human senses. For learners, text-to-speech highlights the holistic scope of NLP, which includes both interpreting human communication and producing it in ways that feel authentic. Ambiguity is one of the greatest challenges for NLP. Words and sentences often carry multiple meanings depending on context. The word bass could refer to a type of fish or a musical range, and the phrase, "I saw the man with the telescope," could be interpreted in more than one way. Humans resolve such ambiguity effortlessly, drawing on context, knowledge, and intuition. For machines, this is far harder. Even advanced models can misinterpret meaning if context is limited or misleading. Addressing ambiguity requires sophisticated embeddings, attention mechanisms, and sometimes hybrid reasoning. For learners, ambiguity illustrates why NLP is so difficult and why progress requires constant innovation to bring machines closer to the flexibility of human understanding. Bias in language models is another pressing issue. Because these systems are trained on large corpora of human-generated text, they absorb not only useful patterns but also harmful stereotypes and prejudices present in that data. A biased model may produce offensive or discriminatory outputs, amplifying existing inequalities. For example, it might associate certain professions with one gender or misrepresent minority groups. Addressing this requires careful dataset curation, bias detection techniques, and ethical oversight. The challenge is not only technical, but also societal, since language reflects cultural norms and power dynamics. For learners, bias in NLP serves as a reminder that technology is never neutral, and that building fair systems demands responsibility and vigilance. Multilingual NLP tackles the challenge of enabling models to handle multiple languages effectively. Early systems required separate models for each language, but modern approaches train on multilingual corpora, allowing a single model to translate and interpret across dozens of languages. These systems reduce barriers to global communication, supporting translation services, cross-lingual search, and multilingual dialogue systems. They also highlight the unevenness of progress, as widely spoken languages benefit from abundant data while others remain underserved. Multilingual NLP illustrates both the promise of inclusive technology and the ongoing work required to ensure that AI reflects the diversity of human communication worldwide. Low-resource languages present some of the most difficult challenges in NLP. Many languages lack the large digital datasets needed to train modern models. This creates disparities, where speakers of underrepresented languages may not benefit from the same AI tools available in English, Chinese, or Spanish. Researchers are exploring techniques like transfer learning, data augmentation, and community-driven annotation to bridge this gap. Addressing low-resource language challenges is essential for equity, ensuring that AI does not reinforce existing divides but instead broadens access. For learners, this area highlights the intersection of technology and social justice, showing how technical solutions must align with cultural and linguistic inclusivity. The future of NLP is focused on making systems more adaptable, inclusive, and context-aware. Researchers are working to build models that require less data, reduce bias, and understand language in richer, more human-like ways. Advances in multimodal learning are combining text with vision and audio, creating systems that can interpret meaning across senses. Efforts in explainability aim to make language models more transparent, helping users trust their outputs. The field is also moving toward greater inclusivity, addressing low-resource languages and cultural diversity. For learners, the trajectory of NLP emphasizes that while remarkable progress has been made, language remains one of AI's most challenging frontiers. The journey is ongoing, and its impact will continue to shape how humans and machines communicate. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.